Thanks.
This is Cris, and this is Alex, so don't confuse them.
Hey. Good. So we love Fourier analysis. Why do we love Fourier analysis? I mean, it has this incredible ability to capture properties of combinatorial objects, such as Boolean functions. We do things like extend Boolean functions to the reals and then take their Fourier transform, and convolution turns into multiplication, and we use this to study Markov chains and computational complexity and all sorts of wonderful things. So there's another technique which we're fond of, which Alex and I are sort of trying to import into computer science and discrete mathematics, and it's inspired by Feynman diagrams. So, when physicists study things like, you know, what is the probability, except it's quantum, so what is the amplitude that some quark and antiquark will annihilate and produce a photon and then produce a positron and an electron, they tend to write down these diagrams, and each of these diagrams represents a nice object in linear algebra. So the idea is that each of these edges here is going to be a vector in some vector space. And each of these interactions, these vertices, is really a tensor. So this little node here would be a tensor that takes in 3 vectors and produces some scalar value when you sum over all the indices of those vectors. And then the value of this whole thing, this would be an internal edge where you would sum over all possible vectors that you can have there over some appropriate distribution. And then you would contract this, and then you would get a tensor which sort of takes these 4 things in, and if you connected those things to others, you would sum over them too. And at the end of the day, you would get some complex number. And so that's what those things mean. And typically, there are many different ways that this could happen. There could be other like virtual particles that come out. You've all seen these things. And then you would sum over all possible diagrams to get the total amplitude of this event, which would then be related to, you know, the force between things, or, you know, and that's more than I know about it. Yes.
So the representation that Valiant has for its match case.
Yes, it's
similar.
Yes, it's very similar. Yeah.
Well, he never needs more than 2 dimensions.
Well, that's because he wants things to stay tractable, right? But in general, if I give you a large graph of these tensors, computing this contraction could be difficult, right? Because the partial tensors that you would get if you were partway through could be extremely high dimensional. So you could find yourself summing over an exponentially large number of possibilities. In the planar case, there are these special tricks you can play.
Yeah, sure,
right?
but even in the 2-dimensional cases, matrices will themselves be exponential size in some of them. So here you think of the number of particles as small and the dimension is small. What is the real cause of complexity in these Feynman diagrams? I always thought that just as usual in quantum complexity, the cause for exponential drop in simulating them is just that the number of particles is large, not the dimension of tensors. They're always
Well, so I'm not sure if people have said anything especially clear about the complexity of Feynman diagrams yet, but what I guess what I have in mind is that the graph here would be of polynomial size in terms of the number of nodes and edges, but that if there isn't a nice partition of it, if it has a large width, then it could be difficult to do the contraction. All right, so here are some familiar objects, but expressed in diagrammatic form. I can think of a matrix, a linear operator, as something with 2 wires, an input and an output, and I wire one to the other, and I get the product of those 2 matrices. If I want the trace, I wire it to itself. So for instance, here is the trace of the identity matrix. It's a loop, and if I have d-dimensional vectors, then the value of this loop, the trace of the identity, is d. And that's because I have, in essence, d different basis vectors that could live on this loop. Okay, so every time you see an edge, there's a vector that can go there. Every time you see some sort of object, that's a tensor which will give some value for whichever combination of vectors is entering into it. Yes? That would be the trace of AB, right? If I wired this back there. And then the nice thing is that diagrammatic. No, that would be more copies of them. There would be more A's and B's on the board. Any closed cycle is a trace, and the reason why physicists love these diagrammatic approaches is that a lot of the algebraic identities we're used to become transparent, right? If I wire B back to A, well, the point is you can move everything around on the board, right? And then it would become transparent that the trace of AB is the trace of BA, because I could just slide one of them around over on top of the other. So a lot of the algebraic identities we're used to, or consider the fact that the matrix product, if you have A tensor B times B tensor A, that's the same as, A tensor B times C tensor D, that's the same as AC tensor BD. Well, diagrammatically, it's the same picture. There's nothing that needs to be said.
What's a tensor of these diagrams?
It's one of these things. So this would be, in this case, just a matrix, although I'm treating one of these entries.
What's a tensor product between two matrices? How is it?
They're just next to each other.
Okay.
Yeah. So A tensor B would just be cut this edge. You would have arrows going in and out of A and arrows going in and out of B, and that's the tensor product. So when it works, it's a very nice way to reason, and you get proofs of algebraic things by picture, basically. So Alex and I have prepared a 3-course tasting menu for you of applications of this sort of thing in mathematics and in discrete math and computer science, and we're hoping to find more. So without further ado, the first one I want to show you is a nice integral which ends up being equivalent or proportional to a discrete object called the circuit partition polynomial, which is a polynomial function of graphs. So let me just describe this, this object here. So suppose I have a graph. It's a directed graph. And imagine that at each vertex of the graph, I have a complex valued vector. And that on each edge, I take the inner product. And of course, here's how we define the inner product of complex vectors. We take the conjugate of one of them. And suppose that for the graph now, and for a given setting of these vectors, I take the product of all these inner products. So it's a kind of mixed moment, if you will, because I'm about to take the average over all the vectors.
So what does the direction signify if it's inner product?
The direction, well, if you switch the direction, it conjugates the product, right? So yeah. So for instance, here's x1 inner x2, x2 inner x3, x4, I have both directions, so I have the absolute value squared. All right? So now suppose that I take the average of this product of inner products over all the values that these vectors can take. So I'll let them be independent, and I could choose them from a number of distributions. One might be the Gaussian distribution, where their entries are independent and Gaussian distributed, or if you wish, I'll choose them uniformly from the sphere, from the unit sphere in k dimensions. So then I get this thing. It's a function of the graph and the number of dimensions, k, in which these vectors live. And again, you can think of it as a kind of moment of the joint distribution of these vectors. So what is this beast? How hard is it to compute? One thing I should mention is that it's 0 unless the graph is Eulerian like this one, because I could multiply vectors by a random phase and zero things out unless I have an equal number of things appearing conjugated and unconjugated at each vertex. All right. So now here's another object which you may have heard of. So again, take an Eulerian graph. There are lots of different ways to cover it with directed cycles. So take a generating function of all the ways to cover it with directed cycles. So for instance, cover the edges with Eulerian. It's an Eulerian style covering, yes. Every edge is covered exactly once. So for instance, here there are two of these cycle coverings, one of them containing one cycle, which covers everything, the other containing two cycles. And so here's this little generating function. Yes, the number of cycles. So of course we could have fancier generating functions which count more things, but here we're just distinguishing the covers by the number of cycles in them. So this is a nice little graph polynomial. It's easy to show that it's sharp p hard under Turing reductions from, even for planar graphs, you can reduce from the Tut polynomial. And I can tell you more about that if you're interested. But so it's a nice little object. Well, it turns out that up to a normalization factor, which just depends on the dimension of the space and the degrees of the vertices, the thing I defined before, that average product of inner products is equal to, proportional to, this graph polynomial, which means, if you're interested, that this is sharp p hard to compute as well. Why in the world might this be true?
The k there is the number of cycles again, right? So you take the number of cycles to be the
Exactly. It
dimension
turns out that the thing getting powered up, getting raised to the number of cycles, is the dimension. And, well, that's, we're giving away a bit of the game, but it's for the same reason that a loop has value equal to the dimension. Here I called the dimension d, there it's k, because I reserved d for the degree of the vertices. All right, so, why this nice coincidence between a continuous object and a discrete object? So that's, in a sense, that's part of what we're trying to do with these diagrams, is reduce various kinds of expectations over, random vectors, random matrices, to this nice discrete setting. So we're going to use some notation here that you may or may not be familiar with. So we're going to follow Dirac and write a column vector like that and a row vector like that. And so the outer product of the two, and here I don't know who to name this notation after. It's kind of mixed. But so this is a matrix where its entry alpha and beta is the alpha entry of y times the beta entry of x, so it's that outer product. And I am writing one of these above and one of them below suggestively. This is something that's from the way Einstein notation is used in relativity. The idea is that one of these is keeping track of vectors and the other is keeping track of dual vectors. So for instance, if I take the trace of this and set alpha equal to beta and then sum over all values they can have, then the trace of the outer product is the inner product. So we just take that and put it on the other side. All right. So now, I'm sorry about all the pixels on the board here, but the idea now is to treat this product of inner products we had before as a contraction of tensors. So for instance, here at vertex 1, I have the outer product of x1 with itself. And this object is going to receive, if you wish, an input on this edge and send an output on that edge. And those will be marked by these indices gamma and alpha.
It's going to, you just define it, take the outer product of x1 with itself, because there'll be two inner products.
Exactly. Exactly. Yes. And then here, for node 3, well, this has two inputs and two outputs. So I'm going to take the outer product of its tensor product with itself. So now it has these four indices corresponding to these four edges. Now, the so-called Einstein notation is just a way to avoid writing sum now over alpha, beta, gamma, eta, and delta. So anytime you see two indices that are, anytime you see an index which is repeated, once above and once below, you assume that we should sum over it. So for instance, here's the inner product of two vectors. Here's the trace of a matrix with itself. Here's a matrix product where I wire the lower index of U to the upper index of V. All right. Okay. Yes? You're right. There should also be an expectation over the vectors, and I haven't written that here.
Yeah, but not on the second law, because there is the sum is this.
Well, there's the sum over,
So it's sum over indices, so it should be.
there's a sum over indices and an expectation over the vectors, yes. All right, so how are we going to change this into a diagrammatic form? Well, in k-dimensional space, the expectation of a vector, its outer product with itself, there is 1 over k times the identity matrix. And that's true if V is uniform in an orthogonal basis, but it's also true, nicely enough, if it's chosen on the sphere, and that's one form of Schur's lemma, if you're familiar with that. So actually, for this equation to be true, I don't need to tell you which of those distributions I'm taking the expectation over. It's also true in the Gaussian distribution with the right normalization. And so, for instance, here is a diagram with some matrix A and the outer product of V with itself. What happens when I take that expectation? There's this 1 over the dimension, and then it just gets smoothed away, and you see the trace. And this makes perfect sense, because this is the trace of this matrix times this matrix, which is an outer product. But by the cyclic property of the trace, if you will, I can grab one of these V's, put it on one side of A, the other V on the other side, and now I have the expectation of the inner product of V with AV, and that's the trace divided by the dimension.
So can you explain again, I guess the second line we know, but.
This is a diagrammatic picture of this. Yes,
So
it's.
why do we see that we can? How did you separate the cycles in the diagram? What are the rules according to which you separated this into?
So what I'm saying is that the expectation of this animal is that. Just the identity times 1 over the dimension.
The two were connected by a cycle, A and this.
Right, I guess I'm illustrating that fact. Well, I guess this is actually a proof, because if this is true for all A, then it's true, because I'm taking the inner product with all possible matrices here. But I'm illustrating that fact by saying, you put this here, and if you take the expectation of this diagram, of course, if you can move the expectation into that box, and it just smooths that away, and you get the trace of A. So this is just a diagrammatic picture of this equation. And I claim that because that's true for A, it's also a proof of this. Does that make sense? All right. So the expectation of this is just a line through it. You can remove it if you wish. To put it differently, the expectation of this is a tensor that requires this to have the same basis vector as this does, which is the identity matrix. It's this delta function of the incoming and outgoing vector. All right, so, well, something nice happens if we look at this 4th order object. So here's the expectation over V of the outer product of V's tensor square with itself. And this ends up being, up to normalization, a sum of the two ways to wire two incoming indices to the two outgoing vertices. So here's the This is the identity operator on CK tensor CK, and this is this exchange operator that permutes the two parts of the tensor product. And this isn't hard to see. I mean, it follows because this operator clearly commutes with any permutation, and then it's just you get the normalization by using the fact that it has trace 1. If V has norm 1, or if V is on the sphere. So in general, when you take the outer product of this tensor power with itself and take the expectation over the vector, you get a sum over all ways to take the incoming edges, permute them, and wire them to the outgoing edges. But what that means is that here, for instance, at this vertex, you have a sum over the two ways to match these incoming edges with the outgoing edges. This vertex, up to normalization, becomes this pair of objects. And when you do that at all possible vertices, you get all possible cycle covers.
We should understand this as superposition. Really understand it.
Yes, it's a linear, yes, I mean, this becomes a linear combination of two tensors, one of which requires these to match those, and the other of which requires these to match those. So if you do this at every possible place, you're summing over all possible cycle covers, because each cycle cover is associated with a way to tell me at each vertex, if I come in this way, which way do I leave? So then we get a bunch of loops, one for each cycle. The vectors are, if they're k-dimensional, then for each cycle we go around, we take the trace of the identity. There are k choices of the basis vector you can have on that cycle. So a diagram with t cycles contributes k to the t, and so in that generating function we have k being powered up by the number of cycles there. By the way, I meant to take this away and make you answer it for a little audience participation. If I had real valued vectors, the graph would be undirected, because then the order of the inner product wouldn't matter. All right. I'm going to...
Where does it come up, this kind of moment, mixed moment?
I'm not sure if I think our motivation for looking at this product of inner products may be lost in the mists of time. But we were happy to have this graph polynomial pop out of it. I think, part of it is that it's very easy to come up with random families of random vectors or random matrices that are random to second order, okay? So for instance, Schur's lemma says that if you look at the image of an irreducible representation over a finite group, you take the tensor product of those things with their conjugates. To second order, this looks as if you took matrices uniformly from all unitary matrices, okay, uniformly in the Haar measure. So if you wish, the image of an irreducible representation is pseudo-random to second order, perfectly pseudo-random to second order. So things that are pseudo-random to higher order are called T-designs if they're pseudo-random to Tth order, and they're of interest in protocols for quantum communication or something. So we started just working out what these higher order expectations were, and then we saw this cute thing coming out of it. All right.
Okay, great. So I get to start up the second course here.
Yes.
Anybody wants to ask
Don't worry.
Before the waiter whisks away the plates?
Right after I put you to sleep with the second course, he's going to come back with a third course, and then you can pester him.
The third course is just some mignardises served with the coffee.
All right.
Next one is more on the order of
Okay, great. So I'm going to try to stick with the same diagrammatic framework, but talk about a completely different problem. It's the problem of analyzing a really, wow, it's like I'm looking down at you. It's the problem of analyzing a really beautiful family of estimators for the permanent. So mostly to set notation and to start you on this path towards sleep, let me remind you what the determinant and permanent of a matrix are. So, pick your favorite n by n matrix that has just 0, 1 entries. And then the determinant, well, you know what it is. You sum over all permutations of the numbers 1 through n. And you sum the sign of the permutation times the product of a bunch of elements in the matrix, right? And it's the elements in the matrix that are picked out by that permutation. And if you have a permutation, I'm going to call the elements of a matrix that it picks out, that is, in the ith row, it picks out element pi of I. I'll call that the transversal of the matrix selected by that permutation. OK, so the determinant, sum over all permutations, sign of the permutation, times the product of all the matrix elements in the transversal that it visits. And then the permanent is just the same thing, but without that confusing sign factor. Okay. And you all know the end of this story, which is the one that, looks more complicated is actually the one that has this profound geometric interpretation. It's homomorphic, it's basis independent, and it's computationally tractable. And then there's the permanent, which looks simpler, but well, it has also a beautiful combinatorial interpretation. It's basis dependent, and as far as we know, it's to compute it exactly is of course intractable. And too far away. Okay, so the combinatorial picture for the permanent. One nice way to think of it is, especially in this case that I've focused on, where the matrix just has 0, 1 entries. This exactly counts the number of perfect matchings of the bipartite graph that you take by taking, right-hand vertices that are the columns and left-hand vertices that are the rows, and putting an edge in whenever you see a 1. Okay. Great. So even in this 0, 1 case, the permanent is fantastically difficult to compute exactly. And the reason that it's everybody's favorite computationally intractable problem is that while it's fantastically difficult to compute exactly, it has all kinds of beautiful internal structure. It's randomly self-reducible. And moreover, and maybe sort of shockingly, there is an ingenious polynomial time approximation scheme for this problem. So we have an algorithm that will approximate the permanent to within any degree of accuracy you prescribe in polynomial time. Okay, so what I want to talk about is another approach towards approximating the permanent, and proponents of this approach have given it a very rosy name. They call it algebraic estimators, which is supposed to has this air of mystique about it. Okay, so instead of telling you what an algebraic estimator is, I want to advance one slide and tell you about the Godsil-Gutman estimator. So I'm going to define this by giving you an example. And if you haven't seen this before, you're in for a real treat. This is just an absolute jewel. So again, we'll focus our attention on an n by n matrix with 0, 1 entries. And
Just an example, it's the original.
this is the one. I mean, yeah, this is the quintessential example. That's right. So we have a 0, 1 matrix, and we would like to estimate the permanent of this matrix. And we're going to adopt the following mysterious strategy. What we're going to do is we're going to take the matrix, that's A, and we're going to define a new matrix M in the following way. So all the zeros of A remain untouched. But all of the ones of A, we decorate with a random sign. Okay? So every one of A is independently and uniformly replaced with a +1 or a -1, and the zeros are untouched. And the remarkable fact is that if you take the determinant of this new object and square it, this is a random variable, of course, the expected value of that is exactly the permanent. And this seems very attractive, right? Because clearly this is a random variable that's easy to sample from. And we know how to compute determinants quickly. And we know how to square things quickly. And so, surely those Jerem, Sinclair, Vagoda guys, we're working too hard, right? All that fancy, ingenious Markov chain, this is clearly the right way to do it, right? Another nice thing about this is, while it seems quite ingenious, the proof that it's true is, you flip over an envelope, you just expand the left-hand side, and it magically happens. But to save the envelope, I'm going to actually just write it out here because I want to make some analogies between this proof and some proofs that I want to talk about later on. So what happens? You just do what comes naturally. You follow your nose. You take this expectation and you expand it. What do you get? You get this big expectation. Now it's a sum over all pairs of permutations. and you get the product of their signs, which of course is the sign of the products. And then you get the product of the elements that you visited along these two transversals. Okay. So one thing is clear, if either one of those permutations visits a transverse, ever visits a 0, that kills that term. That's not interesting. And what's even more interesting is that if either one of these permutations visits a position that the other one didn't visit, well, then we have this situation where we're taking the expectation of a product of a bunch of random variables, but one of the random variables appears only once and has expected value 0. So that also kills that whole term. So it turns out the only terms that actually contribute to the sum are ones when the two permutations are the same, and then everything just works out swimmingly and you're all done. Let me introduce just one little bit of notation here. So of course, if we're dealing with just 0, 1 matrices, there are exactly two kinds of permutations out there of interest, right? They're the ones that stumble upon a 0, and so index a term that is 0, and they're the ones that somehow manage to steer always through the ones as they visit the various parts of the matrix. And I'll use this notation, pi is consistent with A, to indicate the fact that pi steers only through the ones of A. And so one way to write down the permanent is just the number of these things. Okay. Great. So like I said, this clearly seems like the right way to go about building an approximation algorithm for the permanent. And the natural question, of course, is that now that we have this estimator that has the right expected value, we need to figure out how many samples are necessary so that by averaging them we can get close to the expected value. One way to do that is to compute the second moment and apply Chebyshev. And if you do that, you find the number of samples you need is essentially this moment ratio. It's basically the second moment divided by the square of the first moment. And in this literature, this ratio is called the critical ratio. So it makes it sound very important. And so the most natural way to try to understand this, or maybe the simplest way to try to understand this, is to try to control this critical ratio. And unfortunately, in 1993, Karmaker-Karp, Lipton, Lovash, and Luby, good, served up some sort of bad news, which is that if you use the estimator we just talked about, then this critical ratio is exponentially big. Okay. So this appears to be a pretty significant roadblock to this technique. But just as they brought the mallet down on this technique, they also served up a little modicum of hope. And they actually showed something really cool. So they showed that, if instead of replacing every one of the matrix with just a random +1, -1 value, you take every one of the matrix and you replace it with a random unit length complex number, then everything goes through just like before. But now they were able to show that the estimator is, it's still exponentially bad, but it's exponentially better. Okay. And so this made people feel like they were on the scent of something good, right? So, surely, we moved up from 1 dimensions to 2. If we just, fearlessly forge forward, something good will happen. So I think it was Alexander Barvanok that asked the next question in the sequence here, which is, come on, surely it's got to be even better if we replace every one with a unit-length quaternion. Okay. And then he even suggested, why stop there? Let's really take it to the next logical level and just look at other higher dimensional objects. So Chen, Rasmussen, and Sinclair answered his initial question in a 2003 paper, and they showed that his idea was a good one. So if you use the quaternions instead of the unit-length complexes, the critical ratio is even better. 3 halves to the n over 2. We're almost there, right? Yeah.
This is the worst variance you can get for, so there exists a matrix that.
Yes, that's right.
That's interesting. It's a very simple matrix. It's just block diagonals of 2 by 2 matrices.
That's right.
So the worst matrix is really the easiest.
Is the easiest one.
Yeah. But probably they are complex.
Yeah, probably you can find more
For
complicated
random
examples.
matrices, it's not so bad.
Yeah.
There's some nice results on random.
Yeah. But for random matrices, also the Markov chain analysis is very simple.
Yes.
Oh, is that true? That I didn't know.
The original Jerome Sinclair paper, which showed that you can
The conductance is
approximate
much
Yep.
also show that you can do it
I see.
random stuff.
Nice. I see. Okay, so Chan, Rasmussen, and Sinclair then took us to the next level. They worked inside an algebra I'm not going to describe, called the Clifford algebra, which is a generalization of the quaternion algebra. And they show, sure enough, as you turn up the volume, as you turn up the dimension, the critical ratio gets better and better. And they actually established that if you could somehow carry out this whole strategy where the algebra that you choose, where the Clifford algebra has a dimension like linear in n, then you've made it. So the bad news is that for Clifford algebras of dimension greater than 2, we don't know how to compute the determinant efficiently. And so again, this seems like sort of a serious roadblock. But Barvanach then had another good idea. So let me tell you about that. So first of all, I just want to point one thing out, which is that anytime you're talking about a determinant over like a non-abelian algebra, you somehow have to be careful even how you define it, right? If you just, why do you have to be careful how you define it? Because what is a determinant? Well, it's this, sum of a bunch of products. But now that you're in a non-abelian setting, the value of these products may depend on the order in which you took the product, right? So now if you just decide that the regular old-fashioned determinant, you're just going to use it as written, this is some strange artificial choice that you have made to visit the products, sort of in row major order. So you can certainly do that. That gives a kind of, I'll call that the artificial determinant. Alexander Barvanach had another nice idea. So he said, well, let's do what comes naturally, and instead of fixing some particular order, let's just average over all possible orders to explore those terms. Good natural idea, right? So this is called the symmetrized determinant. I'll write S-det for symmetrized determinant. And it's just what you think, right? It's a sum over all permutations, sign, and then what's in here, well, the other part of the sum, is just the average of all ways, the average of the products of all ways to visit the elements that are indexed by that permutation. And furthermore, he showed that unlike the artificial determinant, he was able to find an efficient algorithm for computing those symmetrized determinants. And so efficient here means it takes time order n to the d, where d is the dimension of the non-abelian algebra. So it's efficient for constant dimensional algebras. Anyway, so this so this begs to be explored, right? So it's really natural to hope somehow that as you crank up the d, you could find a family of increasingly better estimators for the permanent. Okay. So what I want to talk about today is Barvanach's symmetrized determinant. I have to pick an algebra to play, to open up the playing field here. And the algebra I want to talk about is the algebra of d by d matrices. And how do you play this game, right? In general, you play this game by replacing every element of A with some element drawn from a distribution that you would like to sort of have expectation 0 from your non-abelian algebra. And so the distribution I'm going to work with is Gaussian measure on the algebra of all d by d matrices. So you can just think every individual coordinate is independently Gaussian. Another natural thing you could think about would be Haar measure, for example, uniform. But anyway, so we're going to think about Gaussian measure. And let me point out that even then we haven't really quite specified what we're talking about, right? Because if we fire things up and try to apply our estimator, we first take A, we patch in a matrix now for every element of A, and we then want to take our determinant of this object, which then gives us an element of A back. And at the end of the day, of course, we need to end up with a real number. So there are a couple of natural ways you could imagine coming up with a real number. Maybe the most natural is to take the Frobenius norm of what you get squared. I'm actually going to talk about something which is slightly different. It turns out the analysis for these is essentially the same, but this uses less ink, so I'll focus on this one. And in this case, what we're going to do is we're going to take the determinant of what we get, we'll take its trace, and look at the norm squared of that. And like I said, it turns out that there's essentially no significant difference between these. Okay, so with that choice of the algebra of d by d matrices with Gaussian measure and working with the norm squared of the trace, we're going to focus on these two determinants. This is the artificial determinant, right? And this is a Barvanach symmetrized determinant. And so we show two things. And maybe you can already see that the news is not so good. Okay? So for the artificial determinant, basically we recover the nice results that Chen, Rasmussen, and Sinclair had. So that's great. Unfortunately, for these, we don't know of algorithms that compute them in general quickly. Yeah.
Is it known to be equivalent to the permanent even for quaternion?
Yep. 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 And in the symmetrized case.
But that's again in the worst case of the choice of the algebraic elements.
Yeah, that's right. And for Barvanach's symmetrized estimators, which are our new hope, right? So for these, unfortunately, we find that for constant d, these all have essentially the same exponential critical ratio. Fine.
So wait a minute. So the symmetrized determinant is much worse in terms of the...
Yeah. So somehow when you symmetrize the determinant, you're somehow really throwing out the non-abelian structure that you relied on to pull down, to exploit. I don't know. Somehow it's like you really threw out what was important. It's
Even though you change an algorithm.
Yeah, I'm curious. Okay, so it's fine. We can all feel sort of morose about this a little bit, but the real reason I want to show you this is I want to show you the proof of how this works, which has this sort of nice diagrammatic flavor. Okay, so instead of showing the whole proof, I really just want to focus on the sort of first order business here, which is let's just compute the expected value of this estimator. And what's the timing like here?
The timing is nice to speakers.
Sorry? It's nice to speakers. Okay, great. Okay, so let's just look at just the expected value of Barvanach's symmetrized estimator in this case. And in that case, you can easily work out what happens. Again, you're summing over all permutations that just touch ones in A. And for each such permutation, you're essentially looking at these sort of average covariances you get by visiting the matrices along the way in random orders. So effectively, there's one quantity of interest. I called it A sub D here, and it's the following quantity. So
Everything non-interesting will be cancelled, and the permanent will come up from the same permutation.
exactly. So you end up with a permanent times some factor, and I want to talk about what that factor is.
We'll get the same transversal, but maybe in two different orders.
Yeah, well, that's right. Yes. I mean, in fact, so that's what comes next. Yes. So, another question? Well, okay, I'm sort of cheating you here, right? This is, what's in here is actually, is the square of a trace, is the square of a trace of a determinant. So you're getting the same kind of quadratic behavior. It turns out that that's enough quadratic behavior to do the right thing. And in the next slide, you'll sort of see why. Okay, so you end up with the permanent times this sort of interesting factor. I want to talk about what that factor is. So that factor is the following thing. So imagine you have n random variables that are all d by d Gaussian matrices. And the quantity of interest is where you pick two permutations at random. And then I look at this covariance of the trace of permuting the product according to one permutation and the trace of computing the product according to the other permutation. And so let's just look at one pet term, the example term here. So one term in this sum would be something like this. The expectation, these sigmas are d by d matrices in Gaussian measure. So we're taking the expected values over these guys of this product. And what is the product? It's the trace of multiplying them in lexicographic order times the trace of multiplying them where the second two have been reversed. Let me put a star here. Okay, so how do we analyze this? So what you're about to see should take you back 25 minutes. So let's just look at what happens if I focus my attention on, for example, sigma 2 here. It appears in two different places. And I can sort of push this expectation through and just think about what it does to these two terms. Because the picture that I'm going to paint of this whole object is that it's a big contraction of tensors. And so I'm just going to focus on the tensor introduced by, say, these two copies of sigma 2 here. And for that, I would like to understand what happens if I take the expected value of, say, sigma 2 here. And I'm thinking of this now as a 4 tensor, right? It has...
So wait, sigma is now sigma 2?
Well, okay, any sigma would do. But yeah, think, for example, about sigma 2.
But the ij has nothing to do with the 2.
Yes, exactly, precisely. So that's a little confusing, isn't it? Okay, so sorry. So think of sigma here as any one of these sigmas. Think of sigma as just a random variable Gaussian distributed on the d by d matrices. And so now, if I if I take the tensor product of that with its star, this gives me a little 4 tensor, right? It has two covariant indices and two contravariant indices, and I want to understand what that tensor is. And the nice fact is that that tensor, I shouldn't point to that, that tensor is this. Okay? So this tensor is exactly a cupcap, and remember, in this diagrammatic world, anytime you see a little arc like this is essentially an equality constraint, right? It says the two things that I touch, it can be anything, but they have to be equal. So it's a somewhat nice fact that if you take the average of the tensor product of a d by d Gaussian with itself, it ends up being a very simple combinatorial tensor. It's the tensor that demands that, you know, the two vectors that it sees up here are the same, and the two vectors it sees down here are the same. So we draw it like that. It also imparts a factor of 1 over d.
So what would it, I'm not sure, I believe it's combinatorial is simpler, but what would it be if it was a 2 by 2 random Gaussian? How will the 4 by 4 matrix look like? There's two loops in the
You would have ones in the 4 corners and zeros everywhere else, and a 1/2 out front.
So it will be a low rank matrix. Will be
That's
rank
rank
This
1.
has rank 1, right?
rank 1. So it's
Yeah.
also,
It has rank 1.
Is it expected that and you're taking all of them out? Full rank
It's a rank 1
matrices.
projection operator.
Right, it's actually the outer I mean, it's sort of like the outer product of the fully mixed state with itself,
Yeah,
if you like.
but it's an outer product of things that have. Oh, it's a fully. Wait, 2 by 2 matrices.
So-
In quantum terms, you would say it's entangled because of these things are connected and these things are connected. But it's an outer product of the input vector, as it were, with the output.
So you think of the 2 by 2 matrices as vectors.
Well, the nice thing about tensors is you can move these things around. They can be, you know, linear operators or vectors.
Yeah,
Initially, they
actually,
count full rank, right? A random 2 by 2 unitary is a full rank. You take the tensor product of two of them, and you get something else which is rank 1. That's what I'm trying to
When you
say.
average, yeah.
when you average.
Yeah, when you average. I find it somewhat surprising because when you take vectors, you take the outer product and you average, you get the identity mainly.
Yeah,
The corners of the V2 things of the rest have to be elements of the V1 solution.
Say again?
When you take the tensor product, right, every term is a V2 polynomial, but the corners are the same variable as the V2, and each other rank is variables of the V1, so we just
But also when we say rank here, as a linear operator that takes these things in and puts out those, it has rank 1.
exactly.
If you switched around some of those wires, it would become the proportional identity matrix or the exchange operator, and then it would have full rank.
Yeah, and this is always a kind of ambiguity that we have when we talk about tensors. And actually, I was sort of sloppy before when I said rank 1, right? I mean, it's rank 1 if you think about it as a linear operator that's mapping, you know, V tensor V to V tensor V. And as you say, there are other realizations of that 4 tensor that give it all kinds of different ranks.
Rank is not a good parameter to talk
So-
about when you are doing your Feynman diagram.
That's right. That's right. Okay, good. So now remember how we take the product of the trace of 3 linear operators. Looks like this. These are the products here, and the trace glues the top to the bottom. Similarly here for the starred operators. And now we know what to do, which is that we just figured out that, for example, these two operators here, when I push the expectation to, these two tensors here, when I push the expectation through, become a combinatorial operator. They become a cupcap. So there'll be a wire that will run from here to there, and a wire that will run from here to there. So if you do all of that, that makes this kind of crisscross pattern. You get three powers of d on the bottom because each cupcap has a 1 over d in front. Okay, good. And how do we evaluate such a thing? Well, as Cris said before, essentially each one of these wires imparts an equality constraint, but you can assign the wire any basis vector you want. So every one of these wires imparts a factor of d, and so there's only one relevant feature of this diagram. It's the number of cycles you get. Okay. Each one of those will introduce a factor of d. So in this case, this is the same diagram, but where the cupcaps have been flipped up or down, and the cycle part, that is the multiplication, and the trace term have been moved inside. Okay, and I guess it's good to do this because I'm going to use the same convention for the next couple of slides. This same thing, just where the edges have been turned inside out, right? The cupcaps have been flipped to the outside, and the outer terms that compute the products and the trace have been pushed inside. Okay, so like I just said, this gives a factor of d for each loop in the diagram, and then you can recover that the expected value of this nice moment is 1 over d squared. Okay, but of course, what we really want to compute is not an individual one of these, right? We want to compute the expectation of this kind of covariance averaged over all various ways to visit these families, over all various ways to multiply together these terms. And an individual way, now it's in white, okay? So an individual way, when we expand this out to n terms, has this part inside that you'll recognize. This is the product of all of these terms, product each one to the next, with the trace connecting the front to the back, same here. And the two permutations that we're talking about, alpha and beta in the original terminology, give a rule about how you wire these vertices here to those. It's by some permutation. And if you look at the whole diagram here, and remember that there's exactly one feature that we care about, which is the number of cycles we get in this diagram. What you can see what's taking place here is that you have a little commutator. So this thing here looks like a rotation map, right? Each of these +1 mod n. There's some permutation in here, and we get the rotation map, a permutation, the rotation map backwards, and the permutation backwards. So this is a commutator. It's a commutator of the permutation alpha, which is actually the product of the previous ones, and the rotation map. And what we care about is the expectation over alpha of d to the number of cycles that appear in this. Okay. So this is what we care about. And the nice part of the story comes next. The nice part of the story is that we actually have a way to exactly analyze this using harmonic analysis in the symmetric group. And if you're familiar with that technology, actually it's quite clear why. So the reason is that the function d to the number of cycles in a permutation, it's a class function. It depends only on the conjugacy class of the argument. And because it's a class function, I can introduce an extra conjugation in here, and then it turns out that this is also actually the convolution of a class function with itself. It's the convolution of the uniform distribution on n cycles with itself. Okay. So I don't want to spend a lot of time on this because if this technology is not familiar to you, this won't give you any traction. But what I would like to get across is once we have the diagrammatic picture, then it's actually quite straightforward to use the representation theory of the symmetric group to compute the inner product of these two class functions. This one, it turns out, is the character of a very beautiful combinatorial representation whose Fourier transform is known. And this one is the convolution also of a distribution that's very well understood. And one nice thing about this is that it's a distribution that has very small support in the Fourier spectrum. So it's only supported on hooks. So it turns out this is quite easy to analyze, and it gives you, and you can exactly compute it down to the line. Okay, so I just want to say a few words about what one actually has to do. Right? What I just showed you was just the first moment calculation. What you really care about is computing the critical ratio, which is the second moment. And I'm not going to go into any details here. I would just like to say that just as in Chris's first course, one has to look at a moment of a kind of 4-tensor of these. And it turns out that what emerges is really quite nice. Instead of being a combinatorial tensor, it's a sum of 2 different combinatorial tensors. And this makes the analysis a little more complicated. It turns out now what happens is you get this slightly more complicated picture. You have these 2 sets of cycles, and it turns out that the picture you had before is now a picture where you're still working inside a, still the relevant objects look like commutators, but now one of the things appearing in the commutator is a product of 2 cycles, and this makes the Fourier analysis more complicated. And in fact, in this case, we don't know of a way to exactly pin the answer. We can only give a lower bound. So to end on a sour note, yeah.
When you don't get the exact expression, it just goes into this error approximating the permanent, goes into the error term?
No, and what we're trying to do here is understand the critical ratio. So what we end up doing in that case is lower bounding the second moment. So unlike for the first moment where we know we can compute exactly what it is at the end, here the harmonic analysis, the Fourier analysis turns out to be a little more messy. We can't.
The upper bound the ratio, but then a range to the d.
Well, actually, we want to lower bound it. Upper bounding it would have been great, but it. So this proves a lower bound on the critical ratio of Barbanach's estimator, showing that if you want to show that Barbanach's estimator works, either it doesn't, or the second moment isn't enough, right? I mean, it's conceivable that Barbanach's estimator really does work, but the second moment isn't strong enough to prove it, right? So the distribution has some crazy structure where the second moment happens to be big, but for some strange reason, most of the time it's close to what it should be. But so this shows that the second moment method won't work to show that Barbanach's.
Well, also it doesn't have an algorithm. I mean, the algorithm is m to the d. I mean, you need
So only constant d.
only constant
Yeah.
d, but it seems like it would be very good even if the second moment, even if the second moment was linear, you still don't have an algorithm for this particular estimate.
Exactly. I mean, yes, maybe the most you could hope for, even if you had something like, 2 to the n over d or something. I mean, even so, this wouldn't compare with the best estimators we know. So anyway, I'll end with a nice with a question. Is there an algebraic estimator which actually is simultaneously concentrated and efficiently computable? Okay, so now Cris does the last course.
Okay, this is very brief, I promise. I told you it was just a quick dessert. Yes?
Yeah. But the algebraic approach, so the macro chain approach only works for matrices that have a non-negative element. So what about the algebraic approach? Can it work for matrices with a negative element?
Absolutely. So in fact, the algebraic approach in general, you can scale. In principle, you could imagine scaling up to a larger family of matrices.
Well, larger but not negative. I mean, the square root embedded there in the, I mean, you talked about 0, 1. But if you have matrices, let's say with non-negative and with aij something, in the estimator you have to take that square root. So if it's negative, you cannot do that. So this algebraic approach doesn't work for matrices directly in any way, with matrices with negative end. Moreover, computing the permanent, or even approximating the permanent, for matrices with negative entries is efficiently hard.
That's connected to algorithms anyway.
Yeah, so you can ask a weaker question.
Okay, so for this last little bit, so the usual way that we choose nearly random elements of groups is by taking a random walk, right? We have a set of generators, And we choose a bunch of things independently from that set of generators, and then we take the product. And if that set of generators has nice properties, for instance, if averaging any non-trivial representation of the group over those generators gives an operator a small norm, then this random walk is rapidly mixing. So it's fun to think about other ways to choose random or nearly random elements of groups. So one would be to fix a set of group elements and then change the order in which you multiply them together. And intuitively, if the group is highly non-abelian in some sense, and if you took enough of these elements, you should get you might get something like a uniform distribution over the group. So here is a smaller version of this question. So for simplicity, I'm going to take G1 through GT uniformly from the entire group. What I really want is taking it from some generating set. But then I'm going to ask, let's look at the pair. I take the product of these group elements, and then I take them again, but in some order, some permutation of the T things. And then I'd like to know, when are these two products nearly independent of each other? So when is this pair almost uniform in G cross G, the set of all pairs of elements? And then a related question, if pi here just is the reversal, and then I take inverses, then this is like taking the product of a bunch of things, G comma G inverse, which you've looked at in perfect groups, right? So we can ask, for instance, when is this set of pairs, and again for simplicity, I'll let G range over the entire group, when is this set of pairs a good expanding set, a good generating set for G cross G? So we're just going to use the same fact we used before, that if I have an irreducible representation of G, I'll call it sigma, and I apologize if you don't know what those are, but we'd love to tell you if you're not already familiar with them. If I average sigma tensor sigma star over a group, I get this Cupcap. And again, this is just another version of Schur's lemma. If I average sigma of G tensored with sigma of G inverse, I get this exchange operator. So it reverses the order of the tensor product and has but both of these have a factor of 1 over the dimension in front of them. So that immediately tells you that suppose our group is quasi-random. So I think this is a term that originated with Gowers. You can think of this as a highly non-abelian group. Its smallest non-trivial representation, irreducible representation, has really big dimension. So for instance, some of the groups that we like for generating excellent expanders, like PSL2Q, for instance, has its smallest non-trivial representation is really huge. It's very non-abelian. In that case, 1 over D is small, and these operators both have small norm. And that's kind of all I'm saying. So in particular, this set here, if D is large, all of these operators have small norm, so this is a good expanding set. But the other thing you can do is you can take these permuted products and wire them up using these cupcaps and practice making Bézier splines on your favorite figure drawing program. And so we can analyze any product, any pair of products we like, and we can take them in a variety of different permutations, and we just have to wire these things up together. If we have a loop, then we get a factor of D, and otherwise we have a factor of 1 over D in front of each thing. So this thing, if you take the expectation over 3 group elements, you get 1 over D squared times the identity matrix on G cross G. Whereas here you get something proportional to the Cupcap. So the upshot of all this is that the set of these pairs is an expander for G cross G, where the eigenvalue depends again on the number of cycles in this commutator. And if you feel like making this random, the permutation uniformly random among all permutations of T things, then we can get a nice upper bound, and we see that this eigenvalue goes down very fast, like 1 over the factorial of the length of the product. So this is something that we would like to think that similar techniques can say something about fooling branching programs over groups. We're kind of at an early stage in thinking about that, but it's something we're very interested in pursuing. So at least for pairwise independence, these diagrammatic techniques work very well. If you want to think about 3 products or more, you have to start thinking more about the structure of the group. But for pairwise independence, all that matters is the dimension of the representations. It's relatively independent of the structure of the group. All right, so just to conclude, if you're playing with random vectors or random matrices, and in some cases random group elements, we hope that we've demonstrated that some of these diagrammatic methods can turn various kinds of averages or integrals into nice combinatorial objects, which you can then, in many cases, hammer down with discrete Fourier analysis. And I will just end with a shameless plug. Lots of people think that you should buy this book. Thank you very much.